I hope you're all having a nice breakfast, lunch, or a dinner break. And for your dining entertainment, it's really a great pleasure for me to introduce Rob Fender to all of you. Some of you obviously know him, but he's currently the head of astrophysics at the University of Oxford. And as you've heard from Alex's talk just recently, there's really great potential to study other objects like X-ray binaries with the ngEHT. And I think Roger Blanford was the first to actually say that X-ray binaries are quasars for the impatient. These sources are really amazing. They do everything that AGN do, but really on these short timescales. So they're very valuable for our studies to understand the physics. And Rob's name is basically synonymous with the radio studies of X-ray binaries. He led some of the first multi-wavelength studies, and these actually helped us derive things like the fundamental plane, the mass relation for AGN that Neil Nagar was mentioning in his talk. But in the meantime, Rob has been pioneering the exploration of the transient radio sky. He's been innovating the kind of blind searches we normally think of for optical facilities like the Vera Rubin Observatory, ZTF. He started out with LOFAR and then the AMI Large Array, but currently he's one of the 2 PIs of ThunderCat, which is a large project to study transients with the SKA Pathfinder MeerKAT. And this is going to directly inform the future SKA work. So today he's going to talk about jets from stellar mass black holes from launch to termination. There you go, Rob.
Great, thanks, Sarah. You can introduce me anytime. That was fantastic. Yeah, so thanks very much for the invitation to the meeting. It's been extremely stimulating so far. In fact, I really knew nothing about the ngEHT project until the invitation a few weeks ago. So yes, it's been very interesting. As Sarah says, my talk's going to build a little bit upon what Alex Tetarenko said in the previous session. So let's move on then. So I want to say first just a little bit about stellar mass black holes in general and their place in the mass and physics spectrum compared to the other black holes which we've been discussing here at this meeting and elsewhere. So the obvious point about the stellar mass black holes, and the one that's obvious to everybody who works on projects like EHT, where your focus is very much to look at the horizon, and the one that's also popped up immediately following and during Alex's talk, is that because of the extremely low mass compared to objects like Sagittarius A star and M87, you're never going to resolve the event horizon. So these things are about 10 solar masses. The heaviest one we know is probably the one that James Miller-Jones was involved in upgrading, Cygnus X1, to about 20 solar masses last week. The distances of the best studied objects are between 1 and 20 kiloparsecs, so they're all within our own galaxy. We know of examples of these objects in other galaxies, but of course that just makes the problem worse. And the horizon size is absolutely tiny. You're never going to do horizon scale physics on these black holes with the Event Horizon Telescope. However, even though you cannot resolve the horizon, you can make exquisite connections to the flow of matter very, very close to the accretion flow. And that's because we're able to separate the accretion flow, the inner accretion flow around the black hole, by observing in X-rays. And as those of you who work in X-rays know, there are exquisite X-ray observations of these sources. There are timing and spectral observations of these sources, very high count rates, very well measured spectra and spectral variations on very short timescales. So we're able to separate out the changes in the accretion flow, and then we're able to connect them to the activity of the jet, crudely, but often by just looking at radio light curves and comparing where we see radio flaring to changes in the accretion flow, and then more productively, and I hope perhaps an angle that EHT and ngEHT can help us with, actually tracking components in the very inner jet and ballistically tying those things back to connections to changes in the accretion flow. So we really can tie the jet production to events that occur very, very close to the black hole. But the way we do that is by combining our radio millimeter with X-ray observations. I'll say a little bit here about the mass spectrum. So if we're looking at black holes masses going from left to right, then the black hole, I call them here the electromagnetic binaries, the X-ray binaries, they certainly contain black holes which are descendants of long GRBs. So the the explosive collapse of massive stars into stellar mass black holes, and probably also in the case of the short GRBs, although the single merger remnant we have from the LIGO neutron star merger 1708-17 is actually a lower mass than the broad spectrum we have for the masses of the black holes in these binaries. And then of course at higher masses we have the LIGO black hole binaries with masses maybe 20, 30, 40 solar masses, and then through some not very well-known process these things grow to be active galactic nuclei through some combination of accretion and mergers. The accretion and jet physics spectrum is very relevant for these objects. So here you'll see I've removed the LIGO black hole binaries because, as you know, we essentially haven't seen these objects accreting, so we can't say very much about them. Starting by moving to the right from the X-ray binaries, then we know through a range of studies, and I'm not going to touch on this here, but there's a large literature on this, that the physics we see of the connection between accretion and jet production is very scalable with mass between the X-ray binaries and the active galactic nuclei. And I'll put the caveat here that this is scalable with mass in a regime which is more or less Eddington limited. So most of the time when we look at these X-ray binaries, and also indeed most of the time when you look at AGN, then we see that the accretion process seems to be more or less Eddington limited. There's probably, in fact, there's bound to be some connection between the physics which we're learning by looking at the X-ray binaries and that which is involved in jet production, both in the long GRBs and in the short GRBs, because we're looking at the same mass and physical scales. But somehow this is going to be turned up to thousands or millions of times super Eddington for very short periods of time. So there's some mysteries here, but there must be clues to the puzzle of what's going on with the GRBs also in studying the X-ray binaries. Okay, so what I want to do actually, so those of you who have seen me talk before will probably be expecting right now to see one of these Q-shaped or turtle head diagrams where I talk through the various connections between states as observed in the inner accretion flow and the jet production. But I don't want to do that. What I want to do actually is I want to talk through a recent example of a new binary which was discovered just a couple of years ago, MaxiJ 1820 plus 070, which has an exquisite data set which really shows how, with new data on a very large range of scales, we can really track these relativistic jets from a black hole all the way from the moment of their launch in the accretion flow all the way out to where they terminate after they decelerate in the interstellar medium. There's some heroes of the piece. In fact, there's a whole bunch of heroes of the piece, but these are the youngest guns associated with this work, and each of these has led an important paper on this source or is shortly about to. So Callum Wood is an undergraduate at Curtin working with James Miller-Jones. And his work was already also briefly mentioned by Alex in her talk. Matilda Espinas and Francesco Caratenuto are PhD students working with Stéphane Courbel in Paris. And Joe Bright is a PhD student, or was a PhD student, who just completed with me in Oxford last year and is now doing a virtual postdoc at Northwestern with Raffaele Margutti. And these people have really led a lot of the important work on this source. Okay, so first off, let me tell you a little bit about what we're doing in ThunderCat. So ThunderCat is a project which Sarah alluded to, which is led by myself and Patrick Wout at the University of Cape Town. And what we're doing is we're surveying the sky on a weekly cadence where we're pointing Meerkat in short snapshots at any source which we have an indication either via optical or X-ray reports or monitoring is in an active state. And when I say any source, I mean X-ray binary source. So what you're seeing here is a movie of about the first 2 years of data from ThunderCat, and every time you see a new frame, that's at about weekly cadence. The source I'm going to be talking about is this one which is handily removed north of the plane, MaxiJ 1820. And those of you who know the field will see some other old favorites in here, so like GX339-4 and GRS 1915. So what you should take away from this is the fact that the sky is continuously active with outbursting nearby black holes. It's not just that these are rare events, or it's only the background AGN which are varying. Continuously within our own galaxy, we see stellar mass black holes producing these relativistic ejection events. Okay, so first off, I'm going to start on the closest scales to the black hole in this source, and I'm going to work my way all the way out to the most distant point from the black hole. So in some sense, becoming less and less relevant for EHT as I do so, but I'll pop back to the closest scales at the end of the talk. So in the case of Event Horizon Telescope, you're trying to disentangle the accretion flow and the jet, which are both emitting at the same wavelength. So this is, this is one of the, you're making beautiful images, but one of the problems you have is you don't really know when you see the emission, whether it's the accretion flow or whether it's the base of the jet. In these X-ray binaries, as I say, we very much know that the X-rays are coming from the very inner accretion flow, typically within about 10 gravitational radii of the black hole, and that the radio is coming from further out. So what you see in the left-hand set of panels here is 6 days in July 2018. And this was a few weeks after this source, J1820, had first been discovered. So highlighting first this top panel here, and if you look at the top panel, the panel marked A, then you see over a 6-day period, you see a rapid increase in the overall X-ray flux, and then something of a cliff around here, around the region where you see the gray bar and the red line. If you look at the lower panel, panel B, this actually indicates the ratio of the X-ray counts in 2 different bands. So essentially when this goes up, this means the X-ray spectrum is hardening, or if you like, the plasma is becoming hotter. And what we see around the time when this steepening occurred in the X-ray flux is that the X-ray spectrum became much hotter. Now, to give you some idea of the temperatures we're talking about here, when the accretion disk is dominating the flux in these sources, the temperature is around 2 keV. When the spectrum is at its hardest, the accretion disk, the accretion flow rather, appears to be dominated by a Comptonized corona with a temperature of about 100 keV. So we have a range of something like 50 or 100 in the very high temperatures of this inner accretion flow. And then around the time of this increase and then hardening in X-ray flux, we were seeing a decline in the radio flux. This is the 15 gigahertz flux observed by the Amy telescope in the UK. But around the time when we saw this dramatic hardening, we saw the beginning of a radio flare at 15 gigahertz, which peaked a short time later and then faded away. And then the overall secular decline, which had been seen before and afterwards, continued. I'm going to zoom in now to the 2-day period around July 6 and 7. So that's the period between the dotted lines in the left-hand panels. So this is just a 2-day period now. And what it means when it says time gaps removed is that there are gaps when the X-ray observatory isn't observing. So we've just taken those out. So this is not strictly speaking linear in time. What you see, first of all, in the top panel here is the soft X-ray flux. In the middle panel, you see the hard X-ray flux, or the moderate, if you like, X-ray flux. And in the lower panel, you see the hard X-ray flux. And this very much demonstrates that the change in the X-ray flux was really due to a hardening, an increase in the hard component of the X-ray spectrum. Most dramatically, and there's a huge amount of information encoded in this plot in the lower right, this is a grayscale of the X-ray power spectrum in the frequency range 0 to 20 hertz. So when you see a lot of black smudges, that means there was a lot of power, a lot of variability on these timescales. You can see coherent structures, which we call QPOs, which are drifting to higher frequencies, which we think means that our disk was moving in from probably a few tens of Rg to a few Rg. And then around the time when the radio flare begins, all of this broadband X-ray power collapses away, and all of the variability in the accretion disk is in a feature at about 5 hertz. So to put this in context, the X-ray accretion flow was varying across a wide range of timescales, and suddenly it's only oscillating the entire accretion flow on a timescale of about 5 seconds. And this is a particular type of QPO we call a type B QPO. This type B QPO ended precisely at the moment when the radio flare was observed to begin. So that's your connection to very close to the black hole. So these results have already been shown by Alex. So let me just move through them quite quickly. These are results produced by Callum Wood, who, as I've said, is an undergraduate at Curtin. So first off, Callum made some short timescale observations with VLBI around the time when we were seeing this radio flaring and this change in the accretion flow. And he saw this component A, which moved between two different epochs, and probably a counterjet component B. So I'll highlight these components here. However, these data were actually analyzed after we looked at larger scale radio jets. And we saw that these jets are moving at probably something like 0.3 C. And that's a problem because we know on slightly larger scales at the same time scale and in days that followed that we were seeing components which were moving much faster, in fact, with superluminal apparent speeds on scales observed by eMerlin, the VLA and ngEHT. But what Callum did, as Alex has already described, is he shifted the phase of these observations so that it matched with the higher proper motions we saw on larger scales, and he recovered this component C. And this component C corresponds to a component ejected with the superluminal speeds we're seeing on the larger scales at exactly the moment that the flare peaked. And essentially, if you track these components back to their launch time, we see that what happened is we have this fast component moving at greater than 0.9 C, which will have moved through the slower component, which is moving at about 0.3 C. This is fantastic. We've never seen anything like this before. Looking at these jets then on larger scales, we actually tracked these jets out for over half a year. This is a sequence of ngEHT and VLA images put together by Joe Bright and published recently by Joe. So we see this beautiful sequence of images as the jets propagated out a long way from the core. We had a very extensive set of radio monitoring flux observations of these core components as they moved away from the core. I'll just highlight some phases here. So there was an initial very rapid decay of the flux from these radio components, which almost certainly corresponds to adiabatic expansion. They started small, they expanded rapidly, they lost a lot of their internal energy. There's then a long protracted period when they're fading, but they're fading relatively slowly. And we believe that what was happening here is they were decelerating, and this results in some transfer of their kinetic energy to in situ particle acceleration. There was a jet break here, which may correspond to the geometrical jet break seen in GRBs in an off-axis generalized sense. And there was a beautiful epoch here where we observed simultaneously with ngEHT and eMerlin at the same time, at the same frequency, but with a huge difference in angular resolution. And we saw that 80% of the flux observed with ngEHT was resolved out by eMerlin, which told us the exact physical scale of the 1.4 gigahertz emission, which allowed us to do a good energy calculation. The jets were also observed in X-ray, so we detected optically thin synchrotron emission all the way from the centimeter radio band through to the few keV X-ray band. And again, this is, this has been done a few times before. This is pretty spectacular. I'll make a note in passing, which is that the radio through X-ray spectrum, as I've said, it's consistent with optically thin synchrotron radiation. And there's really no evidence for any dependence of the spectral index on the bulk Lorentz factor. And this is actually something that was invoked in trying to understand the afterglow of the neutron star merger 1708-17. So putting the whole picture together there, we have this slightly complicated plot on the right-hand side, which is the evolution of the ejector from 1820 over a period of 1 year. And we now see that on larger scales, the ejector have been very clearly on both sides observed to decelerate and to decelerate at an increasing rate as they interact with the material in the interstellar medium. And then, of course, all the really exciting stuff for you guys who like the stuff near the event horizon happened in those first couple of days, where we saw the ejection of components at different speeds connected to the change in the accretion flow. So the ngEHT, of course, could contribute to understanding the first few moments of the jet launch, but then these later observations allow us to do very good calorimetry of the total energy which was contained in the jet. And then we can take this calorimetry and we can track it back, and we can use ngEHT observations to ballistically say exactly when that happened. And we can take the kinetic energy lost from the region near the black hole and connect it to what was happening at that time. And I'll make a point also that these launch events can be anticipated in advance. It's not luck that we get VLBI observations of these things. There is another example by Francesco Caratenuto of deceleration. So this is another source which started going off about 6 months later, where again we observed components associated with a core radio flare propagating out at superluminal velocities. In fact, in this case, we saw a second component. We saw a rebrightening and a rapid deceleration, which is probably some equivalent of the Sedov phase, as these blobs are snow plowing through the interstellar medium. So this stuff is not rare. Okay, so I want to make that point. It's not that you would have to be supremely lucky and have a response time for a TOO of maybe 1 day or so with ngEHT. We can actually see these things rising, and we can plan campaigns. So I'm going to step back now closer to another black hole. This is V404 Cygni. This is these are data from June 2015. Alex already showed this movie, which is 2-minute VLBI observations put together by James Miller-Jones and herself. And we see spatially resolved components on a milliarc second and sub-milliarc second scale. Alex also showed this. These are data which are taken essentially at the same time, up to frequencies as high as 666 gigahertz with the JCM2. So what we can see first off is that for sources such as this, flaring in the ngEHT bands would actually reach several Jansky. So these are going to be bright sources. The other thing is that Alex kindly looked at these data and carefully put together for me 4 sequences where she thought she could track a flare from peaking at the highest millimeter frequency all the way down to centimeter frequencies. What I was able to do then is I can do an equipartition analysis where I assume that each of the peaks I see at each frequency corresponds to the peak corresponding to synchrotron self-absorption. And we're pretty certain that's the case because we see the spectral evolution. And I can see the size of these blobs as a function of time as they propagate out from doing the equipartition analysis. And these blobs are moving only mildly relativistically, so we don't need to make much of a relativistic correction. So first off, what we see is that the expansion speed of the ejector between 2 adjacent peaks is something like 0.1 c. So these blobs are not expanding at the free expansion rate of an ultra-relativistic plasma, but are expanding in a somewhat constrained way. And remember that we know from the VLBI images that they're moving away from the core with a speed of about 0.4 c. So we have, we have a broad opening angle, but these things are collimated to some extent. The key thing here is knowing exactly how long after the launch the millimeter peaks occurred. And this is something that I was motivated to look at, amongst other reasons, by the reports, I think not universally accepted, that there might be a parabolic structure in a structure to the jets, in fact, in M87 and in some other AGN. So if I assume that the 660 gigahertz peak occurred only 13 seconds after launch, which is very optimistic, then I see that the size of the blob as a function of time and as a size of the distance from the black hole, this is log 10 units of RG, went like this, and actually is broadly consistent with a parabolic width increase followed by a conical width increase. And what I draw on here are angular scales. So this is about 1 milliarc second. That's why you can observe these components with centimeter VLBI. That's about 1 AU. And that's about 100 microarc seconds. So here and then some region to the left is the ngEHT and EHT spatial resolution zone. And the vertical line here is the same angular resolution, but put onto the horizontal axis. So you can see whether or not you'd be spatially resolving or even resolving out these ejecta.
Rob,
the launch time, sorry?
Give a few minutes if you want time for questions. So.
Okay, all right, I'm about to finish. Putting the same bar on horizontally then, I said that. So if they're launched, in fact, 10 times later, then you get something more like linear expansion. And if they're launched at about 1,000 seconds later, which may actually be the most likely time, then there's more like linear expansion. But then you see that you would be clearly seeing, you'd be spatially resolving away from the black hole with EHT the times when these blobs peaked to synchrotron self-absorption, which would be very nice. And I'll make one point that I always have to make when I give these talks, which are that neutron stars make relativistic jets too. Don't be going thinking that only black holes make relativistic jets. These are a recent sequence of VLBI images of Scorpius X1, which is the canonical neutron star source. They're part of a 72-hour global VLBI program led by Sarah Motter. And we see components propagating at mildly and ultra relativistic speeds away from the neutron star in this case. Okay, so to wrap up then, in terms of the physics that we're now probing with our observations, the key thing is the connection to the accretion flow. So we can track relativistic ejections from the moment that they're born in the accretion flow by studying in X-rays, and this happens at a few RG. We can track them through a long phase of in situ particle acceleration as they propagate outwards, and then we can finally see them as they decelerate and transfer all their initial kinetic energy into in situ particle acceleration. And these really are exquisite data with which to test models applied to all of these different jet sources. Prospects for ngEHT, Alex has been thinking about this as well. The thing that occurs to me is ngEHT or even EHT really could respond to monitoring programs, or in fact could even target sources which we know are more or less perennially bright. And if you can observe the inner components as they peak to synchrotron self-absorption, as they move away from the black hole, we know that we can do some physical analysis of their physical size. They're always going to have a brightness temperature of about 10 to the 11K at that moment. And to compare that to their ejection and their proper motions and track that back to the variations in the accretion throw, I think would be lead to some very interesting science. And I'll stop there. Thank you.
Thank you very much, Rob. It's a really good talk. Do people have any questions already? Please raise your hand. I see Michael.
Yeah, thanks so much. This was fantastic. I was curious, what fraction of the time do you have multiple components when you're studying these systems in the radio and submillimeter? For the ngEHT, we'd probably only be able to do relative position referencing. There's a chance that we could get absolute phase, especially if the structure is pretty simple, but to really track the motion, if you're dominated by, say, a single bright component, I think would be much more challenging.
The answer is that I can think of sources where you would probably have multiple ejections plus the core black hole within your image at any given moment. And there are also sources which in some sense are cleaner and would, in some sense we could arrange times where you're just seeing a single component propagating away. So there are a few black holes, and one of them is almost perennially active, is this source GRS 1915, which go through phases where they're ejecting powerful blobs every 15 or 20 minutes or so. Okay, so in a sequence of EHT observations, you would probably see a sequence of blobs moving out. That's rather atypical behavior. In your typical transient, you'd probably see just one or maybe two ejector. On the other hand, I say it's atypical, but this is a source which is, it's pretty much on all the time. So we can gear this for either scenario, really.
Thanks.
Okay, Demos, nice to see you. You have a question?
Yes, nice to see you too. You showed that there is a parabolic expansion up to a distance of about 1 million Schwarzschild radii and then linear. So this is a binary system, correct?
Yeah, I wouldn't say I
What's
showed
the size of the binary?
the physical separation of the binary.
In Schwarzschild radii, yes.
Oh, in Schwarzschild radii, physical separation of the binary, I'm not sure.
Well, tell me in centimeter, I will do the conversion.
Very good. It's about 10 to the 11, 10 to the 12 centimeters. In this case,
okay, it's about the same size as, because that's a black hole, right? It's a 10 to the 6. Yeah. The Schwarzschild rate is about 10 to the 6 centimeters, or maybe a few times 10 to the 6. And by the time you go to 1 million, that's about 10 to 12. So that's we're talking about the same sizes here, right?
Yeah.
So the binary plays a role in this collimation.
Possibly.
Okay.
Yeah, I don't know.
Otherwise, I don't see any reason why all of a sudden it becomes conical from the parabolic. But anyway, something to have in mind. Thank you.
Let me add, thank you for your question. I mean, let me add the caveat, this is one possible solution. What we really don't know is exactly when the high frequency peaked. Probably, and somewhat disappointingly, probably that's a more likely scenario right now. But who knows?
Okay, thanks.
If no one else has a question at the moment, I have a question actually, or maybe it's more of something you could go into a bit more detail about the timing of these, the ejecta in J1820. And this is something we discussed a bit with Colin, but I thought for this group here, it might be interesting because basically you're seeing the disk go from being a kind of low luminosity state, and then it's ejecting a slower blob in terms of the timing. And then it seems to go through some sort of chaotic thing, these type B QPOs, and it becomes higher luminosity. And then you get this faster ejecta, right? And so I was just wondering, you know, in this community, we talk a lot about the sane versus mad and the transition to different types of accretion states. Yeah, I mean, what more can you say about that? Do you think that, you know, because people have also said type Bs are precession or something else. So
yes, I think type Bs aren't precession. Type Cs are probably precession. So I can say,
yeah.
I can say a bit more. So in fact, let me scroll back to the X-ray thing. So if you look at the 6-day period around the time when the launch occurred, what was happening is that there was a gradual change in the X-ray spectrum and change in the radio properties, which we understand from looking at, you know, tens of other sources, probably correspond to a transition from a geometrically thick ADAF-like, possibly hot accretion flow, to something that looks more like an accretion disk. And we know that that seems to correspond to the jet being turned off around that time. And we know if you look at the lower right figure, we know, you know, there's good circumstantial evidence from this. You can also, for this, you can also fit the radii of accretion disks, but you see that features in the X-ray power spectrum are drifting to higher frequencies during this period of time, which suggests a region becoming smaller. Exactly what happens when the type B QPO takes over is very dramatic. We don't really know. I mean, it's actually more, as you know, it's more dramatically illustrated if you look at a stack of power spectra. All the broadband power disappears, and only thing that's happening is the accretion flow is oscillating at one frequency. So it looks like towards the end of this this hot, hard state, some kind of slow but powerful ejection came out. And then just around the time when the accretion disk was really oscillating very hard, then a much faster ejection came out. What I really want to know, you know, as you know, these results are hot off the press and are not even submitted yet. I really want to know whether or not we can see any signature in the radio or elsewhere of these two blobs actually colliding with each other. The faster flow, it seems, unless, you know, there's a lot of acceleration going on, it seems that the faster flow must have moved through the slower flow on its way out, which I think is fascinating.
Does anybody else have any other questions? Well, if not, I think we're on to another break. So thanks again, Rob, for your talk and virtual clapping.
You're welcome. Thanks.
And I'll hand this over back to the LOC.